Okay, Dr. Srijith, can you start?
Yes, I can.
Okay.
Okay. So I'll just go to the presentation, right?
Yeah, we'll just give a brief introduction and then we'll start off.
Okay.
Good afternoon, one and all. I'm R.S. Krishna, Junior Scientist at NATPAC. It gives me immense pleasure to welcome you all to the fifth talk of Transpedia Research Talk Series organized by the KSCSTE National Transportation Planning and Research Center, NATPAC. This talk series is yet another unique venture of NATPAC, designed to explore diverse topics from cutting-edge technologies to sustainable solutions. We will be featuring eminent researchers to share their valuable insights in the spirit of research and development in transportation. Today, we have with us Dr. Srijith Balakrishnan, Assistant Professor, Faculty of Technology, Policy and Management, Technical University, Delft, Netherlands, for sharing his valuable insights on the topic, resilience mapping on road networks using traffic data. Before we begin, I would like to invite Sri Wilson Casey, Senior Scientist and Head of Highways and Bridges Division, to deliver the welcome address. Over to you, sir.
Thank you. A very good afternoon to all of you. Myself, Wilson Casey, working as a Senior Scientist in NATPAC. It brings me immense pleasure and honor to extend a heartfelt welcome to each one of you gathered online and offline today for the fifth episode of KSCSTE-NATPAC's esteemed Transpedia Talk Series. This series, initiated by KSCSTE-NATPAC, envisioned to promote research for shared benefits by disseminating knowledge on diverse topics from cutting-edge technologies to sustainable solutions. I think all of aware of KSCSTE-NATPAC. Those who are not aware of KSCSTE-NATPAC, KSCSTE-NATPAC, an institution under Kerala State Council for Science, Technology and Environment, is a premier R&D institution in the country which works in multi-modal system of transportation covering road, rail, water, air, etc. Since its inception in 1976, the center has been handling research and consultancy projects as per the country's bar states requirements. Our journey through this enlightening Transpedia Talk series has commenced with the guidance of and wisdom imparted by Professor Dr. Tom V. Matthew, our RC chairman, setting the stage for a series brimming with the promise. We have been privileged to delve into the expertise of luminaries Dr. Suvin P. Vendiruthi and Dr. Sonu Matthew, each contributing invaluable insight to our collective understanding. Today marks yet another anticipate the illuminating discourse by our distinguished speaker, Dr. Srijith Balakrishnan. Dr. Balakrishnan joins us from TU Delft, Netherlands, generously sharing his expertise on resilience mapping of road networks using traffic data. His commitment to innovation and scholarly contributions promises to enrich our understanding and shape the future landscape of transportation research. Following Dr. Balakrishnan's presentations, we have a question and answer session. Your active participation is key to fostering a meaningful dialogue and leveraging this opportunity to gain deeper insight into the subject matter. Once again, on behalf of the entire Transpedia Talk Series Organizing Committee and NATPAC, I extend a warm welcome to Dr. Srijith Balakrishnan. Thank you all for gracing us with your presence today. Let us embrace this opportunity for learning, collaboration, and the advancements of research in the transportation domain. Thank you all.
Thank you, sir, for your amiable welcome note. Now, I would like to invite Dr. Praveen P.S., Junior Scientist at NATPAC, to introduce the speaker to the audience. Over to you, Praveen.
Thank you, Adra. Dr. Srijith Balakrishnan is an assistant professor with the Transportation and Logistics section of the Faculty of Technology, Policy and Management at TU Delft, Netherlands. He is interested in developing and applying generic and infrastructure-specific frameworks, models, and metrics to evaluate the risk and resilience of interdependent infrastructure systems. While his primary focus is on infrastructure systems modeling and simulation, he is also interested in understanding how infrastructure systems can be designed and managed to enhance the overall well-being of cities during normal and stress conditions. Srijith completed his doctoral studies in transportation engineering at the University of Texas at Austin in August 2020. Prior to joining Delft, he was a postdoctoral researcher at the Future Resilience Systems Division of the Singapore ETH Center, where he contributed to projects involving the simulation and analysis of interdependent infrastructure networks. He has also worked as a short-term researcher at the Oxford Program for Sustainable Infrastructure Systems, University of Oxford. Previously, he was involved in several projects funded by government agencies such as the Texas Department of Transportation and the National Research Foundation, Singapore, in the domain of infrastructure resilience and management. He holds an undergraduate degree in civil engineering from the University of Kerala and a master's degree in civil engineering from the Indian Institute of Technology, Madras. Over to you, Dr. Srijith.
Thanks a lot for the welcome and introduction. Can you see my screen?
Yeah.
Okay, all right.
Yeah.
Thank you. Okay, all right, thanks. So as already mentioned, today's topic is mapping resilience of road networks using traffic data. Just a minute. So it's based on, this talk is based on a study that we conducted as part of my PhD back in Texas. And the structure of the presentation is as follows. I'll first introduce the problem, and then we will get into the study objectives. Then we discuss the different parts of the methodology. And later we will delve into the analysis and results. Finally, I'll summarize the results, the findings. So, as you know, transportation networks are very critical to disaster management, especially during and immediately after disasters, natural disasters like hurricanes, floods, etc. It facilitates evacuation. It helps in restoration of critical infrastructure systems such as power, water networks, and other emergency response of infrastructure. However, on the other hand, transportation networks are also highly exposed to these natural disasters and are highly vulnerable as well. And therefore, the traffic dynamics during disasters, even though is significantly affected by the direct damages inflicted by these natural disasters, it can also be due to a number of reasons. For example, when natural disasters occur, like we of course have transportation infrastructure disruptions, for example, road damages or inundated road links. Like natural disasters can also affect trip decisions of people because of evacuation and emergency response mechanisms. If there are some road damages, if there is huge influx of evacuees, there could be changes to the traffic management patterns, because of which we can have road or lane closures, etc. And all these factors would affect the traffic condition in the network. And transportation network resilience is one quality that would actually affect how the system recovers from these fluctuations. So I'm sure that you all have heard of the term resilience. It's getting a broader attention these days due to the increase in the intensity and frequency of natural disasters. So resilience is actually the ability of a system to reduce the chances of an external shock, absorb such a shock if it occurs, and recover quickly after that particular shock. And the figure on the right shows a typical resilience curve. It essentially shows the performance of a system during and after a disaster. So a disaster happens here at this point, and then because of damages or due to other indirect impacts, the network performance comes down. And then once the recovery activities are initiated, like the system slowly starts to go back to its normalcy. And as far as transportation network is concerned, the spatio-temporal variations in traffic parameters can effectively capture the resilience of the system. For example, when there is a natural disaster like flood, maybe some of these road links are flooded, because of which there won't be any traffic movement. And that gets reflected in different traffic parameters that we know. For example, traffic speed, traffic density, and traffic flow. And these traffic parameters can also capture how quickly the system recovers and go back to normalcy. And that will also have an impact on the network parameters. And the premise for this study is Hurricane Harvey, which occurred in 2017 in southern United States. So it was a Category 4 hurricane which affected southern and eastern US between August 25th, 2017 and September 2nd, 2017. Even though it was a Category 4 hurricane, the precipitation that followed was quite intense in the Houston region, with some parts even receiving around 40 inches of rainfall, which is around approximately 100 centimeters of rainfall. And the total estimated economic loss from this hurricane in Houston region was approximately $125 billion. One of the other characteristics of this hurricane was that it actually involved mandatory evacuation in coastal Texas, especially in the Galveston region and the Houston region, because of which there was huge temporary displacement of people affecting the transportation network. And of course, because of the intense rainfall, hundreds of road closure events were reported in Houston as well. So all these factors affected how the Houston road network functioned during the hurricane. And the objective of this study is to map the initial impact and recovery of the Houston freeway network during Hurricane Harvey. And for that, we use the traffic data available in that region. And of course, the study also had some specific objectives. Of course, the first one was to develop a method to quantify the initial impact and recovery of the transportation network in Houston during Hurricane Harvey. And for this, we adopted a how worse rather than a how good approach to quantify the hurricane impacts and recovery. And this is contrary to the usual method that we use for quantifying the traffic performance or traffic reliability. We have traffic reliability indices and all, which actually tells you how good the network is. But here we are adopting a how worse approach. And of course, it's a bit challenging when we use traffic data to study the effect of external events on the transportation networks, because as you know, traffic data such as traffic speeds, traffic density, traffic flow, etc., are affected by the seasonal and long-term trends. For example, we have time of the day variations in traffic data, as well as day of the week variation. So these things are also these factors also need to be considered. So here is the overview of the methodology that we have adopted. This is an imperial study because we are using actual historical data to study the effect of Hurricane Harvey. And of course, it involved data collection. We needed 3 different types of data. And then, of course, like the data was not complete, so we had to do a bit of pre-processing. And as I mentioned in the previous slide, traffic data involves spatio-temporal variations like seasonal variations and trends, and these have to be segregated from these other variations so that we can actually study the effect of the hurricane on the network. And for that, we had to adopt some time series decomposition techniques. And later, we developed a few metrics to quantify the effect of the hurricane on the transportation networks, and then we applied to study how the Houston freeway network performed during the hurricane. And the first step is the data collection, and as I mentioned before, we needed 3 different types of data sets. The first one was the Houston freeway network. Of course, there were other road networks for which we didn't have the traffic data, so we focus on the freeway network instead of the whole network. And the freeway network consisted of 485 links belonging to major highways in Houston. And then the freeway network was, some of the links were actually in the freeway network were designated as evacuation corridors, as shown in the figure in blue color. As I mentioned in the introduction, like there was mandatory evacuation from the southeast and southern parts of Houston, and because of which a lot of people temporarily moved to the cities of San Antonio and Austin in the west and Dallas in the north, because of which there was some impact of the evacuation on the network as well. For the study, the network, Houston Freeway Network data was retrieved from the Houston Transtar website. The second type of data that we required was the road closure event data. We obtained the road closure information related to the Hurricane Harvey from Texted Houston office. So the figures show the distribution of the road closure events. For example, as you can see on the top left figure, like high water events, construction events, and maintenance were the primary reasons for road closures during. Excuse me. All right. So high water events, construction events, and maintenance events were responsible for most of the road closures during the hurricane. The second figure on the top right shows the road closure durations. And if you see, most of the road closures were around like 10 to 20 hours. However, you can also see that there were a few high water events which caused road closures for almost like 400 hours. So that's like 15, 16 days, I guess. And on the bottom, you see like you also see the road closure events and when each of the road closure event was started. And you see, I have marked the duration when the landfall of the hurricane happened in Houston in gray. And you see that there are a lot of high water events during that time, and then a lot of road closure events with unknown reasons immediately following that period. The third type of data that we required was the link level travel time data. For that, we relied on the Houston Transtar speed map archive. So that's a collection of average speed data, which are available from January 2009 for every 15-minute interval. So we have the 15-minute average travel average speed for each of the 485 links on the freeway network. And on the bottom, you can see a typical link travel time series that we obtained from the speed archive. Of course, we had to transform the speeds into the link travel times, which is a very trivial task. The next step was pre-processing of the data. We had to do a bit of data cleaning and imputation for the travel time data because some of the links didn't have any data for the entire time period. In some cases, there were like periodic missing data. There was some random missing data across all links in some cases, and some random missing data which were link specific. So we adopted some appropriate imputation methods to resolve these issues. Now we get into the data analysis. As I mentioned before, like the travel time data, it has seasonal components and trend components. For example, we always see the time of the day and day of the week variations in travel time data sets all around the world. So we had to actually segregate it from the rest so that like we can study the impact of the hurricane. And for that, we used time series decomposition method. So what it does is it actually splits the observed travel times into trend, seasonal component, and remainder, where the trend will indicate the long-term gradual travel time changes, which can be due to some land use changes, or maybe some due to some induced traffic flows. The seasonal component captures the day of the week and the time of the day fluctuations, and the remainder captures the short-term fluctuations due to traffic incidents. So during normal periods, there can be accidents, there can be some temporary road closures, which may last for a few minutes, and those are actually captured by remainder. On the other hand, when it comes to that hurricane week or during the hurricane week, the period of landfall and immediately after that, what we expect is that the remainder component will also capture the travel time variations, which were induced by the hurricane, which could be either due to flooding or due to some changes in the traffic management mechanisms, etc. And you can actually use different types of decomposition methods. There are a lot of these methods available in time series analysis. However, we use the seasonal trend decomposition using loss method for this particular case. One of the reasons why we used this technique was that it offers greater flexibility in choosing the seasonality characteristics, and also it has that innate capability to handle missing data. So of course, like even though I presented that data imputation and data processing separately, like it's done in the study, it's done together using this STL technique. And decomposition using STL technique was implemented using the forecast package in our statistical software. Now, once we actually split the observed travel time into 3 components, now the next step is to identify the extreme travel time observations. You might be remembering that I mentioned that here we actually, in this study, we adopt an how worse approach rather than a how good approach. So if we want to know how worse the system or the network has performed, we actually need to study the extreme travel time observations. So in this study, we define extreme travel time observation as a 15-minute observation that deviates significantly from what is expected to be normal for a given time of the day and day of the week. And in order to identify the extreme travel time observations, we used a statistical test called generalized extreme standardized deviate tests. These are essentially used to, this method is very popular in a lot of areas to identify outliers in a univariate normal data set. Applications include areas such as cybersecurity, social media analytics, etc. And what this test do is it checks if there are up to a specific percentage of outliers in the data set. And using a statistical test, it defines whether a particular outlier is statistically significant or not. So here is what we did using that decomposition and the GEST test. So in the first step, we actually split the observed travel time series into the trend, seasonal, and remainder component. And then we applied the GEST statistical test on the remainder time series to obtain the extreme travel time observations. And as you can see here, you see that the part that is marked in the brown color, that is essentially the landfall week of the hurricane. And you can see that the density as well as the size of these outliers are higher compared to the normal events preceding that week. So it gives an indication that the time this method works. So once we identified the extreme travel time observation, the next step was to develop some metrics based on these extreme travel time observations to capture the effect of the hurricane on the road network performance. So in order to, so these metrics are relative in nature. That means that we actually compare some of the characteristics of these extreme events during the landfall week with the normal weeks. So for this, we split the whole data set into two. We selected 8 weeks, 8 normal weeks between June 16th, 2017 and August 10th, 2017. And the hurricanes weeks are designated as the 6 weeks between August 11, 2017, which is around this time, and then and until September 21st, 2017. So that means that we actually consider 2 weeks before the landfall of the hurricane as a hurricane week, because what we expect is that there could be there could be warnings, there could be hurricane tracking, and because of that, some of the people may start to evacuate in the weeks before the landfall. And we developed 3 different types of metrics. As I said before, they are relative in nature. We compare the quality of the one characteristics of these extreme travel time observations during the hurricane week with a normal week. The first metric was the relative change in number of extreme travel time observations, which essentially gives us an idea about like what's the duration of these extreme travel times were observed in the field. On the other hand, the second metric tells us the relative change in mean size of extreme travel time observations, which tells you how worse that those 15-minute 15-minute intervals were during the hurricane week compared to a normal week. And then we also have a third metric, which indicates the average deviation in travel time delay during a hurricane week compared to a normal week. And now we get into the results. So we have the 6 hurricane weeks, as I mentioned before. And here the figure shows the absolute number of extreme travel time observations. So you can see that on week 0, which is essentially the hurricane landfall week, there were a huge increase in the number of extreme travel time observations, which tells you how many 15-minute intervals were actually abnormal compared to a normal week. And you can see that in some of these links in the week 0, there were almost like 600 extreme travel time observations, which is essentially 150 hours, or like that's like 7 days. So, and also you can also notice how the network actually are affected due to the hurricane landfall and how it goes back to normalcy. By week 3, you can see that the number of extreme travel time observations have come down in most of the links compared to the week 0. Similarly, we have the second metric, which is the absolute mean size of extreme travel time observations. Here also you see how it varies over the hurricane weeks, and we saw that like the number of extreme travel time extreme observations were higher during the hurricane week. However, when it comes to the mean size of these extreme travel time observations, we can see that week 1 was most affected. So that means just after the landfall happened, and maybe the recovery may have just started. So, all right, so now we actually combine these 3 metrics to study how the network actually were truly impacted and how the recovery happened. So as you see, these figures, each of the figure represent a particular week. On the x-axis, we have the second metrics, which is the relative size of the extreme observation. And on y-axis, we have the relative change in the number of extreme observation, which is essentially the first metric that we discussed. And you can see that like on week 0 and week 1, there have been very significant variation in these extreme travel time observations compared to week -2 and week 3. So and also you can see that on week 0, the number of the number of extreme travel time observations have been a lot. So that means that that's the week where the network was the most affected in terms of the duration of abnormality. And as far as the intensity of abnormality is concerned, week 1 is most affected because you see a lot of these these links shifting towards the right of the y-axis. And now we also, so though the previous analysis was for each of these freeway links, now what we did was to combine them to their respective corridors, because a lot of these links can be actually combined to combined, and then they can actually reflect how the different highways were functioning during the hurricane. And here is the visualization. So you can see on x-axis we have the deviation in the size of the extreme travel time observation, and on the y we have the number of extreme travel time observation. And you can see how actually the network changes. So this is 2 weeks before the landfall, and you can see what happens now. Like now it's essentially the week of the landfall. Again, like it goes back to normalcy by the 3rd week. So that's what actually captured by these metrics. So so that's all. So we saw 2 different types of temporal trends. The first one is that both number and size of extreme travel time observations followed a typical resilience curve, as we discussed in the introduction section. We can see that the network actually is affected extremely significantly by week 0, which is the landfall week, but then we also saw how it actually comes back to normalcy. And as far as the variance in mean size of extreme observation is concerned, the trend is slightly different. We saw that there is much more variance in these mean size of extreme travel time observations. The previous week of the landfall and the week that followed the landfall. So what we can infer is that before the landfall occurred, there could be a lot of there was a lot of evacuation, because of which actually many of these roads were really congested, leading to delays. And on the other hand, the week that followed the landfall, maybe people were actually coming back to their respective resident areas. So that could also have led to a huge increase in the traffic in many of the corridors. So that's all the metrics and the results. And now one of the applications of this metric is of these resilience metrics is to identify the worst affected corridors. So we of course we know these are quantitative metrics, so that like each of the links will have a value for every hurricane week. So we know like in which hurricane week, which link was most affected or which corridor was most affected. So the table shows we were also able to identify the most affected corridors in the Houston freeway network based on these three metrics. So yeah, that's all the study. So to summarize, this study developed a few metrics, three specific, to analyze the disaster impacts on road networks and subsequent recovery. So the variations due to both the direct and indirect impacts of hurricanes could be captured by these matrices. And this, in a way, reflect the true resilience of the network compared to a simulation-based study where we cannot capture all the effects in one model. And then there are a few potential disaster management applications for the metrics. It can help in improving existing evacuation plans, because we can identify which of these links or corridors were most affected due to the influx or the outflow of people due to evacuation or ingress. Also, it can help us to enhance traffic management strategies. For example, we clearly know which corridors are most affected by the flooding or traffic, and then that can be actually used for improving existing traffic management practices. All right, here I would like to also acknowledge Houston Transtar and Texas Department of Transportation, who provided the data sets, which were very critical in the study. That's all. I hope you enjoyed this talk. Thanks a lot for joining. And if you have any questions, I can definitely jump in. Thank you.
It was an enlightening talk. Thank you. Now the forum is open for discussion.
Yeah. Thank you, Dr. Srijith. It was a nice talk. I understand that good participants are there. Somebody wanted to ask me interact with the Srijith, probably that you can do it now. From outside also, yeah, there.
Am I audible?
Yes.
Yeah. Hi, Dr. Srijith. This is Dr. Vasudevan.
Hi.
A small doubt. In order to identify these, the variations or the evacuation in this network, did you use only the travel time, or any other parameters that can be identified as, to estimate these variations rather than the normal days?
Yeah, thanks a lot for the question. And yes, we only had this data, travel time data, actually speed data, 15-minute speed data. Of course, like ideally, we would also like to know the flow so that like we could distinguish the reason why these travel time fluctuations happened. For example, some of these links were actually flooded, inundated, actually for a week or so. But some of these links were also they had longer travel time because of actual influx of vehicles. So since we used only travel time, like we were not able to distinguish the reason behind it. So that's something that should be done, but then unfortunately we didn't have access to that data.
Okay. Thank you. Thank you.
So I think I'm not really sure whether the Houston Transtor collect they actually store the flow data as well. But what I know is that they actually use these Bluetooth sensors. They use some short distance Bluetooth-based sensors to match the vehicles. So definitely they would have some idea of the flow. I know that they also sample it like one in like 20 or like 1 in 50. I'm not really sure about it, but they don't really collect the travel time speed of all the vehicles. But still, I think there might be some way they might have some information on the flow, but that's not really publicly available. For the public, it's just the 15-minute speed that's available.
Right. Thank you.
Srijith, this is Sanjay from NATPAC. Hope I'm audible. Yeah. Okay. Very nice presentation. So you're focusing on maybe like a plan mapping the resilience and the related things. So would you advocate any kind of planning perspectives from the study that you have done? Like what would be the way forward in planning aspects?
So yes, so for us, like it was just mapping. We had the data, and then we also provided this the findings to Textert, but we are not really sure how they actually have implemented. But I think I already summarized how it could be actually applied in real world, like because it was a historical event and it was a very an event which actually created a lot of impact, the whole network. So definitely we know like which of these if we go further, if we actually combine the flooding data and other data, we can definitely know like which of these links were actually really flooded, or like which of these links were actually which were really affected by these evacuation and other traffic management changes. So I think that gives us a better understanding to solve some of the pertinent issues pertinent issues that they face during hurricane. For example, one of the common issue that they face is that during hurricanes is when evacuation happens, many of the times they didn't pre-stage enough materials in terms of food or like fuel, etc. They were not able to pre-stage it through the corridors because that created a lot of other issues in evacuation and even slow down evacuation. So this study can actually help them to identify the corridors that performed really well during the hurricane, and probably make changes to the mitigation strategies, or evacuation strategies.
Okay, thank you, thank you.
Any other questions? Now, how about the accuracy of this data which you are, you have any idea about the accuracy of the data, like a travel time or even the other data? The government is supplying that one, or how it is recorded?
So this one, so I think that they actually do the pre-processing from their end, of course. So what we did was to actually obtain this data from the Houston Transtar Speed Archive portal. So we actually use some scraping tools for this purpose. So on request, they actually provided to us, so we have to assume that it's correct.
Okay.
Yeah. But of course, like as I presented in one of the slides, there were a lot of issues with the data. So we had to go for our own data imputation techniques. And like, of course, like there were like some very abnormal values which we had to correct.
Thank you.
Okay, thank you. Now I call upon Dr. Amisha, Junior Scientist, NATPAC, to propose the vote.
Thank you, Anita. Having surveys to gain deep insight into the dynamic design mapping of network using data delivered by your distinguished speaker, Dr. Srijith Balakrishnan.
Divisha, you are not audible.
Is it audible, sir?
Yeah.
We have been privileged to gain deep insight into the topic decision mapping of road network using traffic data delivered by our distinguished speaker, Dr. Srijith Balakrishnan. Your expertise has not only illuminated our understanding, but also inspired us to look at the data-driven methods to identify traffic fluctuations used by a natural disaster and urban traffic network. We truly appreciate the time and effort you put into preparing and delivering such an engaging talk. I'd also like to extend our thanks to all the attendees for your participation. We hope that you found the information presented today both informative and inspiring. We are very much thankful to our director, Dr. Samson Matthews, sir, for his constant guidance and support in shaping this wonderful event. As we depart, let us carry forward the knowledge, gain, and connection made. May the insight shared today fuel our curiosity and drive for excellence in the field of transportation. Once again, I would like to express our sincere thanks to Dr. Srijith Balakrishnan, the NATPAC team, and all of you for making this technical talk a great success. We look forward to more such enlightening sessions in the future. Thank you. Have a wonderful day.
Thank you, Srijith.
Thank you. Thank you so much.
And we have two regional office, one at Ernakulam and another one at Kozhikode. So she was giving that lesson. The thanks not from regional office Ernakulam. Thank you.
Okay, thanks.